Welcome to our episode of Cellular Respiration. Asian.
Everyone needs energy. Energy can be gained through the foods we eat. Judy is eating apples. Those are healthy energy. Martina is eating cookies. Caution. Do not try this at home. Parents, do not give your children as much cookies as Martina has. But how does our body transform this energy into something we can use? We call this process cellular respiration. Through this process, ATP is ultimately synthesized as a result of a breakdown of glucose molecules.
There are three parts to cellular respiration: glycolysis, the Krebs cycle, also known as the citric acid cycle, and the oxidative phosphorylation with the electron transfer chain. It can get a little complicated, so we'll take this process one at a time.
Next up is the Krebs cycle, or the citric acid cycle. Before we dive into this, we will backtrack a tiny bit to a step called pyruvate oxidation that occurs between glycolysis and the Krebs cycle. During this stage, pyruvate undergoes oxidation, which cleaves a carbon atom from the 3-carbon pyruvate molecule. One CO2 molecule is released and one NADH is during process per pyruvate. During everything, this point happens twice because there's 2 pyruvate molecules. Because of this, pyruvate oxidation actually produces 2 NADH molecules. The newly formed 2-carbon compound is called acetyl-CoA. This is where the Krebs cycle begins.
Acetyl-CoA will create citric acid, a 6-carbon compound. This makes sense. A 2-carbon compound binds with a 4-carbon compound to make a 6-carbon compound. After being oxidized over multiple steps, 2 carbon dioxide molecules are released as 2 carbons that are cleaved from the citric acid molecule, returning to its original state. This is why we call this a cycle. Even though we're skipping over the nitty-gritty elements of the Krebs cycle, there are a few things you should know about it. Upon one completion of the cycle, 3 NADH, 1 ATP, and 1 FADH2 molecules are created. Why do we care about this? We skip over the individual steps of the cycle, but we need to know this piece. Why? These are the molecules that will be input into the electron transfer chain.
Oxidative phosphorylation and the electron transfer chain. During oxidative phosphorylation, NADH is oxidized into NAD plus H electrons. Also, instead of oxygen needed, water is released. This is the process of oxygen reduction. To solve this problem, oxidative phosphorylation makes use of another process known as the electron transfer chain. This electron transfer chain is where most of the ATP is synthesized during cellular respiration. How does this work? As NADH comes in, it donates its protons and electrons and becomes NAD+. Those electrons are received by one receptor, which transfers them to another receptor, which transfers them to another receptor, and so on and so forth. As the energy is released, it is used to pump protons across the membrane from the matrix to the intermembrane space. This creates a proton gradient. However, these protons are very high energy and want to move down a gradient from an area of high proton concentration to an area of lower proton concentration. Because these molecules are so high energy, we can't just let them move through without using that energy to help the cell in some way. This is the perfect opportunity to create ATP using this energy. The way that this happens is through a protein complex called ATP synthase. ATP synthase goes through the membrane and is fairly mechanical in structure. It allows the hydrogen protons to flow down their electrochemical gradient. As the protons flow down their concentration gradient, they spin the axle of the ATP synthase protein. This forms 3 molecules of ATP at a time. Thus, usable energy is created, and that is the process of cellular respiration.
Let's step back and review.
During glycolysis, one glucose molecule is broken down into 2 pyruvate molecules over a series of different stages. One glucose molecule yields 2 pyruvate molecules. A net of 2 ATP molecules are also created. Moving on, these new pyruvate molecules are then transformed into 2 acetyl-CoA molecules through a process called pyruvate oxidation. This process also produces 2 molecules of NADH. We then move into the Krebs cycle, or the citric acid cycle, where acetyl-CoA binds to oxaloacetic acid to produce citric acid. Through a series of steps, the citric acid molecule loses 2 carbons, returning it to its original state as a molecule of oxaloacetic acid. 6 NADH, 2 ATP, and 2 FADH molecules are formed as a result of the 2 cycles, 1 per pyruvate molecule. Up to this point, the process of cellular respiration has produced 4 ATPs, 10 NADH, and 2 FADH molecules. These become the inputs for the electron transport chain. Because the process of oxidative phosphorylation on its own would produce way too much energy all at once, an electron transport chain is put to use. Because of this mechanism, electrons flowing through the chain produce small amounts of energy at a time, in turn powering the pumping of H+ ions across the membrane. These ions then flow down the concentration gradient, powering a protein called ATP synthase to synthesize ATP as its name suggests.